Before you fall asleep tonight, consider this simple, true fact. Right now, the smallest pieces of the universe are behaving in ways no human intuition ever predicted. Yet every experiment confirms them. If calm, real science helps you relax and stay curious, take a moment to subscribe, like this video, and leave a comment about where you're listening from or what part of the universe fascinates you most. Your support helps keep these quiet, evidence-based journeys possible. Now, settle your breathing and let your mind rest as you begin exploring how reality behaves when we look closely enough to measure it. You begin by resting your attention on the simple fact that the universe is layered. There is the scale of daily experience, where objects have clear positions, speeds, and shapes. A cup stays on a table. A stone falls downward. These patterns feel stable because they are governed by physical laws that work well at human-sized distances and speeds. For centuries, these laws form the foundation of physics, describing motion, energy, and forces with remarkable accuracy. As your thoughts settle, you allow yourself to look deeper, toward scales far smaller than anything your senses can directly perceive. At these scales, matter is made of atoms, and atoms are made of even smaller components. When scientists begin to investigate this realm with careful experiments, something unexpected appears. The familiar rules no longer explain what is observed. Light behaves sometimes like a wave and sometimes like a particle. Energy is absorbed and emitted in fixed amounts rather than smooth ranges. Measurements resist precise prediction. Quantum physics grows from these observations, not from speculation. It is a framework built to match what experiments repeatedly show. Whenever classical equations fail to predict results accurately, quantum equations succeed. This is not because reality becomes chaotic, but because it follows rules that differ from everyday intuition. These rules are precise, mathematical, and consistently confirmed. You rest with the idea that quantum physics does not replace classical physics. Instead, it extends it. When systems are large, quantum behavior averages out, and classical laws emerge naturally. When systems are small, quantum behavior dominates, and probabilities replace certainties. This transition is not mysterious. It is measured in laboratories around the world, again and again, using controlled experiments and careful statistics. As you continue listening, you are introduced to the role of measurement. In classical physics, measuring an object does not change its state in any significant way. A ruler placed next to a table does not alter the table's length. In quantum physics, measurement is different. The act of measuring is an interaction. It involves energy, particles, and forces. When a quantum system is measured, it responds to that interaction, and the result reflects this process. This does not mean consciousness affects reality. Measurements are physical events, not mental ones. Detectors register signals. Instruments interact with particles. Outcomes follow statistical patterns that match quantum predictions precisely. Over many repetitions, these patterns become stable and reliable. The uncertainty lies not in nature's behavior, but in which specific outcome appears in a single trial. You learn that quantum mechanics describes systems using something called a quantum state. This state contains all the information needed to predict the probabilities of different measurement results. It does not describe what a particle is doing between measurements in the classical sense. Instead, it provides a complete and accurate account of what can be observed. This shift in description is subtle but important, and it remains firmly supported by evidence. The calm rhythm of the science continues as you consider why this framework matters. Quantum physics is not abstract theory removed from reality. It underlies modern technologies such as semiconductors, lasers, and medical imaging devices. Every time a computer processes information or a phone sends a signal, quantum principles are quietly at work. These applications exist because the theory matches how nature behaves. As your breathing slows, you begin to sense that the quantum world is not strange for the sake of being strange. It is unfamiliar only because it operates under conditions far removed from daily life. At small scales, energy levels are discrete. Interactions happen in quantized steps. Outcomes are described statistically. These features are not philosophical ideas. They are measured facts. The story of quantum physics is also a story of humility. Scientists do not impose meaning onto data. They adjust their understanding to fit what experiments reveal. When predictions fail, theories change. This process continues today, guided by precision instruments and careful reasoning. Quantum mechanics remains one of the most thoroughly tested theories in science, with no confirmed experimental contradictions. As you rest with these ideas, the concept of connection begins to quietly take shape. In classical thinking, objects are independent unless forces act between them. In quantum systems, relationships can be encoded within shared states. This possibility emerges naturally from the mathematics and is confirmed by observation. It does not violate known physical limits, and it does not allow faster-than-light signals. You are not asked to accept anything on faith. Every idea introduced so far rests on experiments that can be repeated and verified. The calm confidence of quantum physics comes from its success, not from mystery. It tells us how nature behaves when examined closely, with honesty about what can be predicted and what can only be described probabilistically. As your attention softens, you remain aware that this deeper view of reality does not replace the world you know. Tables remain solid. Clocks keep time. Classical physics still works where it should. The quantum description simply reveals another layer beneath the surface, one that operates quietly, consistently, and with remarkable precision. You rest in the understanding that the universe does not become less real when examined more closely. It becomes more detailed, more structured, and more carefully understood. At the smallest scales, relationships matter as much as individual objects, and measurement reveals patterns that remain hidden in ordinary experience. With this gentle foundation in place, your mind becomes open to how quantum systems can share properties in ways that challenge everyday intuition, while still respecting every known physical law. In the quiet space where measurement meets mathematics, you sense that understanding deepens not by force, but by careful observation, and that even the smallest pieces of the universe can be linked by structures that reveal themselves only when examined with patience and care. You remain settled in the idea that physics grows from measurement. Long before equations are rewritten, instruments speak first. At the end of the 19th century, scientists believe they understand the physical world almost completely. Motion, heat, light, and electricity all appear explainable using classical laws. These laws work extraordinarily well for planets, machines, and everyday matter. Confidence runs deep, supported by centuries of success. Yet as measurements become more precise, subtle problems appear. They do not arrive as dramatic failures, but as small inconsistencies. Light emitted from heated objects behaves differently than expected. Electrons ejected from metals by light refuse to follow classical predictions. Atoms emit light at specific colors rather than continuous spectra. Each observation is carefully documented, repeated, and confirmed. You notice that none of these results come from philosophical speculation. They come from controlled experiments using improved detectors, refined techniques, and growing attention to detail. When classical equations fail to match the data is trusted. Physics begins to change because it must. One of the first clues appears in the study of heat and radiation. When objects glow, the color and intensity of the light depend on temperature. Classical theory predicts that hotter objects should emit infinite energy at short wavelengths. This prediction is not merely wrong, it is impossible. Measurements show finite, stable results. The mismatch forces a new idea. Energy exchange occurs in discrete units. This proposal is cautious at first. Energy does not flow smoothly at small scales, but in packets proportional to frequency. These packets are later called quanta. The idea feels strange only because it contradicts intuition formed at larger scales. Experiments continue to confirm it. The smallest measurable exchanges of energy follow fixed rules. You allow this to settle gently. Nature is not becoming erratic. It is becoming precise in a different way. Where classical physics assumes continuity, measurement reveals granularity. Where smooth curves once dominated equations, step-like behavior emerges. Another turning point comes from light itself. Experiments show that light can eject electrons from metal surfaces, but only if its frequency is high enough. Increasing brightness alone does nothing. Classical theory cannot explain this. Quantum theory explains it exactly. Light interacts as discrete energy packets whose size depends on frequency. The measurements match the predictions without adjustment. You rest with the realization that light is not being reimagined for convenience. Its behavior is being described accurately. Depending on how it is measured, light displays wave-like or particle-like properties. This is not a contradiction. It reflects how interactions occur at small scales. Measurement defines which aspect becomes observable. Attention then turns inward toward atoms themselves. Classical models imagine electrons orbiting nuclei like planets. But measurements of atomic spectra show that electrons occupy specific energy levels. They do not spiral inward. They transition between allowed states, emitting or absorbing light at precise frequencies. Every line in the spectrum corresponds to a measured fact. These results force a deeper change. Physics can no longer describe particles as having definite positions and velocities at all times. Instead, it describes probabilities of outcomes. This is not a failure of knowledge. It is a faithful representation of what experiments reveal. When predictions are made, they match observed statistics perfectly. You notice how measurement becomes central rather than incidental. The properties of small systems are not revealed passively. They are obtained through interaction. Detectors exchange energy with particles. Outcomes are recorded as events, not trajectories. The theory reflects this structure carefully. The shift does not happen all at once. Each step is cautious, debated, and tested. Whenever quantum predictions differ from classical ones, experiments decide. Again and again, quantum mechanics wins. Not because it is more imaginative, but because it is more accurate. You remain grounded in the idea that uncertainty enters physics not as ignorance, but as structure. Certain pairs of properties cannot be measured simultaneously with arbitrary precision. This is not a technological limitation. It is a fundamental feature confirmed by countless experiments. When one quantity becomes sharply defined, the range of possible outcomes for another expands. This does not make nature unpredictable. It makes it statistically precise. Over many measurements, averages and distributions remain stable. Engineers rely on these principles every day. Technologies function because quantum rules are dependable. As the science unfolds gently, you sense that classical physics still holds its place. It remains an excellent approximation when systems are large. The new framework does not erase the old. It explains why the old works when it does, and why it fails when pushed too far. You rest with the understanding that the very small is not chaotic. It is disciplined by rules that differ from familiar ones, yet remain exact. Measurement does not disrupt reality. It reveals which aspects can be known together and which must be described probabilistically. Through patient observation, physics learns to speak a new language. Not a language of absolutes, but of likelihoods grounded in evidence. Every prediction is testable. Every assumption is challenged by experiment. As attention softens, you begin to sense that once measurement reshapes understanding at small scales, it also reshapes how systems relate to one another, allowing properties to become linked in ways that classical ideas never require. When observation reaches deeply enough, you see that measurement does not merely record the universe. It reveals the structure by which physical properties emerge, opening the door to relationships that exist only at the smallest scales of nature. You begin by letting go of the idea that a particle must always behave like a tiny solid object moving along a clear path. At everyday scales, this picture works well. A thrown ball has a position and a speed at every moment. Its future can be predicted accurately if you know enough details. This expectation becomes deeply familiar, almost automatic. At very small scales, careful measurement begins to show that this picture no longer holds. When scientists try to track individual particles such as electrons, they do not find clean trajectories. Instead, they find patterns. When many measurements are repeated under the same conditions, the results form stable distributions. Each individual outcome varies, but the overall structure remains consistent. You rest with the idea that physics responds by changing how it describes particles. Instead of assigning exact values at all times, it assigns a quantum state. This state is not a guess. It is a complete mathematical description of everything that can be predicted about a system. From it, physicists calculate the probabilities of different measurement outcomes with remarkable accuracy. A quantum state does not say where a particle is in the classical sense. It describes the range of possible positions that might be measured and how likely each one is. The same applies to momentum, energy, and other measurable properties. These probabilities are not subjective. They are verified by experiments that match predictions to many decimal places. You notice that probability here is not a lack of knowledge that could be fixed by better tools. Even with perfect instruments, individual outcomes still vary. The uncertainty is built into how nature behaves at small scales. This is not randomness without structure. It is uncertainty with strict mathematical order. As your attention settles, you learn that some properties are linked in a fundamental way. Position and momentum form one such pair. When a measurement narrows the uncertainty in one, the uncertainty in the other must widen. This relationship is not imposed by theory. It is observed directly. Every attempt to violate it fails in the same consistent way. This relationship is expressed through precise equations. These equations do not describe what is hidden from view. They describe what can be observed. Physics shifts from asking what a particle is doing to asking what outcomes are possible when it interacts with a measuring device. You begin to understand that the quantum state evolves smoothly over time according to well-tested rules. This evolution is deterministic. Given the current state, its future form can be calculated exactly. Uncertainty enters only when a measurement occurs. At that moment, one of the allowed outcomes appears, chosen according to the probabilities encoded in the state. This does not imply that measurement creates reality from nothing. It reflects the fact that properties like position or momentum are not independent of interaction. They are revealed through interaction. Detectors exchange energy with particles. Signals are registered. Outcomes are recorded as events. You remain grounded in evidence as this view unfolds. Interference experiments show how particles behave like waves when not measured for specific properties. Detection experiments show how the same particles appear as localized impacts when position is measured. Both behaviors are predicted by the same quantum state. No contradiction arises. You allow yourself to see that the language of waves and particles is incomplete on its own. The quantum state is more fundamental than either picture. It is not a physical wave in space, nor a hidden object carrying definite properties. It is a tool that connects preparation, evolution, and measurement into one consistent framework. As the explanation continues, you learn that different measurements correspond to different mathematical operations on the quantum state. Choosing what to measure shapes what information becomes available. This does not mean observers control outcomes. It means physical interactions determine which properties can be revealed together. You notice how this description removes the need for speculation. There is no requirement to imagine unseen paths or concealed values. Everything the theory claims is tied directly to measurement. If a quantity cannot be measured, it does not appear as a definite property in the description. This approach proves extraordinarily reliable. Predictions derived from quantum states guide the design of experiments, technologies, and materials. Atomic clocks measure time with unmatched precision. Electron microscopes resolve structures far smaller than light wavelengths. None of this would work if quantum states were incomplete. You rest with the understanding that particles are not undefined or vague. They are precisely described in a way that reflects how nature actually behaves. The shift is not from certainty to confusion, but from classical certainty to quantum precision. As your breathing slows, you sense how this framework naturally allows relationships between particles to be described together. When systems interact, their quantum states can merge into a single description. Individual properties may no longer be separable. Measurements on one part can inform expectations about another. This possibility does not arise from imagination. It arises from the same mathematical rules already confirmed for single particles. When systems are linked by interaction, the description expands to include them as one. You remain calm as this idea settles, knowing that nothing here violates physical law. No signals are sent faster than light. No causality is broken. The theory remains internally consistent and externally verified. In this quiet space of understanding, you sense that the quantum state is not a story about mystery, but a disciplined way of accounting for everything that can be known through measurement. As particles are understood through shared descriptions rather than isolated values, you begin to sense how the structure of quantum states allows connections to exist that are defined not by distance, but by the information encoded within the system itself. You remain grounded in the idea that quantum physics grows cautiously, shaped by observation and consistency rather than imagination. As scientists refine the mathematical description of quantum states, they begin to notice something subtle but unavoidable. When two systems interact, even briefly, their combined description cannot always be separated cleanly into independent parts. The equations insist on treating them as one. At first, this is not framed as a new phenomenon. It appears simply as a feature of the formalism. When particles exchange energy or momentum, the quantum state that describes them afterward often includes correlations between their properties. These correlations are precise. They are not adjustable. They follow directly from the same rules already verified for single particles. You rest with the realization that classical physics expects independence. Once objects separate, their properties belong to them alone unless forces continue to act. Quantum mechanics does not always allow this separation. The shared history of interaction leaves a measurable imprint. The combined system carries information that cannot be assigned to either part individually. This idea becomes clearer as physicists study systems with well-defined total properties. For example, two particles may be created together in a way that conserves momentum or angular momentum. Classical thinking would allow each particle to carry its own definite values. Quantum mechanics predicts something different. It predicts that only the combined values are definite, while the individual values remain undetermined until measured. You notice how carefully this distinction is framed. The theory does not claim that particles secretly hold unknown values. It claims that the quantum state encodes only what can be predicted. When measurements are made, outcomes appear in correlated ways that reflect the structure of that state. This feature begins to attract attention not because it feels strange, but because it challenges assumptions inherited from classical reasoning. If one particle is measured and a result is obtained, the description of the other particle updates immediately. Not because a signal travels between them, but because the quantum state describes them jointly. This leads to deep discussion. Some physicists accept the implication as a natural consequence of the theory. Others question whether the description is complete. Among the most careful critics is Albert Einstein, working with Boris Podolsky and Nathan Rosen. They frame a precise argument intended to test whether quantum mechanics leaves out underlying elements of reality. You remain focused on how this argument is constructed. It does not reject experimental results. It accepts quantum predictions but questions their interpretation. If measuring one particle allows predictions about another distant particle, perhaps each particle carried definite properties all along. These hypothetical properties become known as hidden variables. The argument is not emotional or dismissive. It is rigorous and respectful of evidence. It highlights a tension between quantum mechanics and classical ideas about locality, the principle that objects are influenced only by nearby interactions. The concern is not about speed or signaling, but about whether physical properties can exist independently. You sense that this moment is important not because it resolves anything immediately, but because it clarifies the stakes. The question becomes sharply defined. Either quantum mechanics is incomplete, or nature does not obey classical separability. There is no appeal to intuition. Only experiments can decide. At this stage, entanglement is still not named as such. It exists as a structural feature of the theory. The mathematics allows states where properties are inseparable. Whether this reflects reality or merely an incomplete description remains open. You rest with the patience of the scientific process. Rather than rushing to conclusions, physicists examine what the theory actually predicts. They derive testable consequences that distinguish quantum correlations from any classical alternative. This step takes time, precision, and restraint. The language used remains careful. Correlation does not imply causation. No usable information is transmitted by measuring one particle. Statistical patterns emerge only when results from both sides are later compared. These features preserve consistency with relativity while maintaining the quantum description. You begin to see how the concept of entanglement takes shape through necessity rather than invention. It is not added to quantum mechanics to explain something mysterious. It is recognized because the existing framework demands it. Removing it would break the theory's ability to match experimental results. As discussions continue, the focus shifts from philosophical discomfort to operational clarity. What exactly does quantum mechanics predict for correlated systems? How strong are these correlations? Can they be explained by any model that preserves classical independence? You sense that the scientific community remains divided, but not fractured. Disagreement sharpens analysis. Every assumption is examined. Every implication is traced back to measurable consequences. The goal remains understanding, not comfort. In this quiet unfolding, entanglement gradually becomes recognized as a defining feature of quantum systems. It is not an optional interpretation. It is a statement about how joint systems behave when described accurately. The theory does not allow each part to carry a complete description on its own. You remain calm as this idea settles. It does not claim that particles communicate instantaneously. It does not assign intention or awareness to nature. It simply reflects how probabilities are distributed across measurements when systems are prepared together. As experimental techniques improve, physicists begin to realize that the question is no longer whether entanglement exists mathematically, but whether its implications appear in measurable outcomes. The debate shifts toward designing experiments capable of testing these predictions directly. You rest with the understanding that science advances by allowing uncomfortable ideas to stand long enough to be tested. Entanglement survives this process not because it feels intuitive, but because it remains consistent with every confirmed observation. In this space of careful reasoning, you see that quantum mechanics is not hiding meaning behind mystery. It is exposing structure where classical ideas once assumed independence. Entanglement emerges as a consequence of taking measurement seriously and describing systems as they actually behave. As interaction leaves its imprint on joint descriptions of nature, you sense that some physical relationships persist not through forces or signals, but through the shared structure of how systems are prepared and measured. You begin by resting in a simple clarification. Entanglement does not describe particles influencing one another across space. It describes how they are mathematically and physically described together. When two particles are entangled, the most complete description of their properties belongs to the pair as a whole, not to either particle on its own. This idea emerges directly from how quantum states work. When two systems interact, their states combine. Sometimes this combined state can be separated cleanly into two independent descriptions. Sometimes it cannot. When it cannot, the systems are entangled. This distinction is precise and testable. It is not a matter of interpretation. You allow yourself to move slowly through a common example. Two particles are created together in a way that conserves a physical quantity, such as total angular momentum. The combined system has a definite total value. Quantum mechanics predicts that neither particle individually has a definite value before measurement. Only the total is fixed. When one particle is measured, a specific outcome appears. At that same moment, the range of possible outcomes for the other particle becomes constrained. This does not require any force or signal. It follows directly from the shared description of the system. The quantum state already encodes these correlations. You notice that nothing here violates causality. Measuring one particle does not transmit usable information to the other. The outcome of a single measurement appears random. Only when results from both sides are later compared do the correlations become visible. This comparison always requires classical communication at or below the speed of light. You rest with the idea that entanglement is about correlation, not control. No experiment allows one observer to choose an outcome for the distant particle. The statistics are fixed by the preparation of the system, not by decisions made during measurement. To understand this more clearly, you consider spin a fundamental quantum property. Spin does not mean literal rotation. It is an intrinsic property measured through interaction with magnetic fields. When two particles are prepared in a specific joint spin state, measurements along the same direction always produce opposite results. This pattern repeats perfectly over many trials. Classical models attempt to explain this by assuming each particle carries a hidden instruction set. Experiments rule this out. The correlations are stronger than any classical strategy allows. They follow the exact predictions of quantum mechanics, not approximations. You remain calm as this result settles. It does not suggest anything mystical. It suggests that nature does not assign independent properties to entangled systems in advance. Properties emerge during measurement in a way constrained by the shared state. You notice how careful the language remains. Physicists do not say particles know about each other. They say the quantum state is non-separable. This means that no description assigning definite properties to each particle independently can reproduce the observed results. The structure of entanglement becomes clearer as you consider different measurement choices. If one particle's property is measured along a different direction, the correlation pattern changes. These changes follow precise mathematical rules. The outcomes remain random individually, but the joint statistics remain predictable. You see that entanglement does not depend on distance. Particles can be separated by meters, kilometers, or more. As long as the quantum state remains intact, the correlations persist. Distance affects how measurements are compared, not how the state behaves. You rest with the understanding that entanglement is fragile. Interactions with the environment tend to break it. Noise, thermal motion, and uncontrolled collisions disrupt the shared state. This is why maintaining entanglement in experiments requires careful isolation and precise timing. This fragility reinforces that entanglement is not a vague concept. It is something that can be created, preserved briefly, measured, and lost. Its behavior is governed by well-tested equations. Engineers work with it deliberately, using it as a resource rather than a curiosity. As your breathing slows, you consider what entanglement does not imply. It does not allow messages to be sent instantly. It does not bypass physical limits. It does not require consciousness. Every part of its behavior is consistent with established physical law. The power of entanglement lies in how it encodes information. The information is not stored in either particle alone. It exists in the relationship defined by the quantum state. This is why measuring one part alone gives incomplete information. Only joint analysis reveals the full structure. You notice how this challenges everyday intuition while remaining logically tight. In daily life, objects have properties independent of observation. In entangled quantum systems, properties are relational. They belong to the system as a whole. This does not mean reality is vague. It means reality is structured differently at small scales. The structure is mathematical, testable, and consistent. Once accepted, it explains experimental results cleanly without contradiction. You rest with the idea that entanglement is not an added feature of quantum mechanics. It is an unavoidable consequence of applying its rules to interacting systems. Removing it would require abandoning predictions that experiments confirm. As attention softens, you recognize that understanding entanglement requires patience rather than intuition. It asks you to trust measurement over expectation, statistics over single outcomes, and shared descriptions over isolated ones. In this calm understanding, the idea becomes less unsettling. Entanglement is simply how nature behaves when systems are prepared together and measured carefully. It is precise, limited, and deeply constrained by evidence. As you sit with this clarity, you sense that even when particles drift far apart, the rules governing their shared description remain intact, inviting careful thought about how distance and space fit within the deeper structure of physical law. You begin by resting in a familiar principle of physics. Nothing that carries usable information moves faster than light. This limit is not a suggestion or a convention. It is measured, tested, and woven deeply into the structure of spacetime itself. Every observation of cause and effect in the universe respects this boundary. Signals, forces, and influences all obey it. As quantum entanglement enters the picture, it may seem at first that this limit is threatened. When two particles are entangled, measurements performed far apart show correlations that appear instant. This impression can feel unsettling if approached too quickly. So you slow down and return to what is actually measured. When an observer measures one particle in an entangled pair, the outcome appears immediately on their detector. That result is random. It cannot be chosen or controlled. At the same time, the quantum description of the other particle becomes more specific. But no signal travels between them. Nothing moves through space. No energy is transferred. You remain focused on the distinction between correlation and communication. Correlation refers to a relationship between outcomes that becomes visible only after results are compared. Communication requires a signal that can be used to transmit information. Entanglement provides the first, but never the second. To see this clearly, you imagine two observers separated by a large distance. Each measures their particle and records a result. At that moment, neither observer can learn anything about the other's result. Each sequence of outcomes looks random on its own. Only later, when the data sets are brought together through ordinary communication, do the correlations appear. This comparison step always respects the speed of light. It involves classical signals, such as electronic messages or physical transport of data. Until this step occurs, entanglement produces no observable effect that can be used to influence events elsewhere. You rest with the idea that relativity is not an optional constraint. It is built into how measurements are compared across space and time. Quantum mechanics respects this fully. The mathematical structure of entanglement never allows faster-than-light influence. You now consider spacetime more carefully. In relativity, events are ordered differently depending on the observer's frame of reference. Two measurements that appear simultaneous in one frame may occur in a different order in another. Quantum mechanics does not assign a preferred frame. The correlations predicted by entanglement remain consistent regardless of how events are ordered. This consistency is not accidental. It is a requirement of the theory. The predictions of quantum mechanics are constructed to agree with relativistic causality. Experiments confirm this agreement repeatedly, even when measurements are arranged so that neither can be said to occur first. You remain grounded in the fact that entanglement does not introduce new kinds of influence. It does not modify spacetime. It does not allow shortcuts. It reflects how joint quantum states encode information across systems prepared together. As your breathing slows, you consider a helpful clarification. When a measurement is made on one particle, physicists say the quantum state updates. This update is not a physical process traveling through space. It is a change in description based on new information. The description changes instantly because it is not bound to a location. This distinction matters. Physical processes occur in spacetime. Descriptions do not. Updating a description does not imply motion or influence. It reflects a logical adjustment based on what is now known. You rest with the understanding that quantum states are tools for prediction. They summarize relationships between possible outcomes. When one outcome is observed, the probabilities for others change accordingly. This happens without violating any physical limit. Relativity places strict rules on what can influence what. Quantum mechanics follows these rules exactly. Entanglement does not weaken them. It operates within them. You also consider what experiments show. Tests of entanglement are designed carefully to prevent any possible signal from traveling between measurement devices. Detectors are shielded. Timing is controlled. Distances are chosen to rule out communication at light speed. Even under these conditions, the correlations persist. These experiments do not suggest hidden channels or unknown forces. They confirm that the correlations arise from the shared preparation of the system, not from later interaction. You notice how this understanding removes drama from the picture. Entanglement does not stretch space or compress time. It does not allow effects without causes. It does not bypass physical law. It simply reflects that some systems are described most accurately as wholes rather than as collections of independent parts. As attention settles further, you see how this fits naturally with spacetime itself. In relativity, spacetime is not a backdrop but a structure that shapes relationships between events. Entanglement adds another layer of relational structure, not to spacetime itself, but to the description of quantum systems within it. Distance still matters. It determines how quickly information can be exchanged. It shapes causal order. What distance does not do is weaken correlations that are already encoded in a quantum state. You remain calm as this clarity deepens. There is no conflict between quantum mechanics and relativity here. There is only a challenge to intuition shaped by everyday experience. When intuition yields to measurement, the picture becomes stable. You rest with the idea that entanglement teaches restraint. It shows that strong correlations do not require direct influence. They require shared origin and careful description. Once systems are prepared together, their statistical behavior reflects that preparation regardless of how far apart they later travel. As your mind slows, you sense that spacetime continues to provide the stage on which events unfold, while quantum mechanics describes how probabilities are distributed across those events. Each theory remains intact. Neither overrules the other. The universe remains orderly, bounded, and consistent. Even its most subtle connections obey the same limits that govern stars, clocks, and light itself. As distance stretches systems apart without loosening their shared structure, you are left with the quiet understanding that spacetime sets the limits of influence, while quantum states quietly define how relationships persist within those limits. You remain settled in the understanding that science advances when questions are sharpened enough to be tested. For many years, the strange correlations predicted by quantum mechanics leave room for doubt. Some physicists wonder whether the theory is incomplete. Perhaps particles carry hidden properties that determine outcomes in advance, even if those properties cannot be measured directly. This idea feels appealing because it preserves familiar intuitions. Objects would still possess definite attributes. Measurement would merely reveal what already exists. Correlations between distant particles would reflect shared instructions rather than anything fundamentally new. You rest with the recognition that this proposal is not dismissed lightly. It is examined carefully with respect for both logic and evidence. The challenge lies in determining whether such hidden variable models can reproduce all the statistical predictions of quantum mechanics while still respecting locality, the principle that influences do not travel faster than light. For a long time, this question remains unresolved because it seems philosophical rather than experimental. That changes when physicist John Bell introduces a powerful idea. He shows that the assumptions behind local hidden variables lead to specific mathematical limits on observable correlations. These limits are not vague. They can be calculated precisely. Bell's insight is calm and exact. If particles carry pre-existing local properties that determine measurement outcomes, then correlations between distant measurements must obey certain inequalities. These inequalities are not assumptions. They are logical consequences of locality and realism combined. You allow this to settle gently. Bell does not assume quantum mechanics is correct. He assumes only that measurement outcomes are determined by local hidden variables. From that assumption alone, he derives constraints that any such theory must satisfy. Quantum mechanics predicts something different. It predicts correlations that can exceed those limits under specific measurement choices. The difference is sharp. Either the inequalities hold or quantum mechanics is right. There is no room for interpretation between them. You rest with the importance of this moment. The question of completeness is no longer abstract. It becomes something that detectors can decide. Experiments can now distinguish between competing views of nature. Designing these experiments requires care. Physicists must ensure that measurement settings are chosen independently. They must prevent any signal from traveling between detectors. Timing, distance, and randomness all matter. The goal is to close every possible loophole that could allow hidden variables to mimic quantum predictions. As the first experiments are performed, the results begin to accumulate. They show violations of Bell's inequalities, exactly as quantum mechanics predicts. The correlations are too strong to be explained by any local hidden variable model. You remain grounded as these results are repeated and refined. New experiments improve detector efficiency. Others increase separation distance. Random number generators are used to choose measurement settings at the last possible moment. Each refinement removes another potential explanation based on hidden influences. The pattern remains unchanged. The inequalities are violated. Quantum predictions hold. You notice that these experiments do not show particles sending signals to one another. They do not reveal faster-than-light communication. They show something more subtle. They show that the assumption of pre-existing local properties cannot account for observed correlations. This realization is quiet but profound. It does not say that reality is undefined. It says that certain classical expectations do not apply at small scales. Properties are not assigned independently of measurement in the way once assumed. You rest with the fact that Bell's theorem does not rely on interpretation. It does not depend on how one thinks about measurement philosophically. It relies only on statistical results. Either the inequalities are respected or they are not. Nature answers clearly. You consider how this affects the earlier concerns raised by Einstein and others. Their insistence on clarity leads directly to this test. The result does not diminish their contribution. It honors it. By demanding precision, they help uncover deeper structure. The outcome does not imply that quantum mechanics explains everything. It implies that any deeper theory must abandon at least one classical assumption. Either locality, realism, or both must be revised. Experiments strongly support maintaining locality, leaving realism in its classical form as the assumption that must change. You remain calm as this idea settles. Realism here does not mean reality disappears. It means that physical properties do not exist as definite values independent of how they are measured. This shift is subtle, not dramatic. It reflects what experiments already show. You notice how this conclusion does not introduce chaos. The statistics of outcomes remain stable. Predictions remain precise. Technology continues to function reliably. The world does not become arbitrary. It becomes relational at a deeper level. Bell's theorem does not add new rules to quantum mechanics. It clarifies what the existing rules imply. It draws a boundary around what kinds of explanations are possible. Within that boundary, quantum mechanics stands firm. As your breathing slows, you reflect on how this marks a turning point. The debate moves from whether entanglement is real to how it behaves, from questioning its existence to understanding its consequences. You rest with the understanding that the end of local hidden variables is not the end of inquiry. It is the end of a particular hope for restoring classical intuition unchanged. What replaces it is not confusion, but a clearer picture shaped by evidence. You remain grounded in the experimental nature of this conclusion. No single test decides the matter. Hundreds of experiments across decades contribute. Each adds weight. Each confirms the same pattern. The calm strength of this result lies in its simplicity. When assumptions are tested, nature responds. The response is consistent. Quantum mechanics continues to match reality where alternatives do not. As attention softens further, you sense that entanglement is no longer a theoretical curiosity. It is a verified feature of the world, one that reshapes how relationships between systems must be described. The universe does not conform to expectations formed at larger scales. It conforms to its own structure, revealed patiently through measurement. As classical assumptions quietly fall away under the weight of evidence, you are left with the steady realization that the deepest connections in nature are not hidden behind unseen variables, but revealed directly through patterns that measurement itself brings into view. You begin by imagining a space designed for patience. A laboratory built not for speed or spectacle, but for control. Temperature is regulated. Vibrations are damped. Stray electromagnetic signals are shielded. Every effort is made to reduce unwanted interaction because at small scales, interaction is everything. Entanglement cannot be tested casually. It must be created deliberately, under conditions that allow its effects to stand out clearly from background noise. Scientists begin by preparing quantum systems in well-defined ways. This preparation step is crucial. The correlations later observed depend entirely on how the system is created. One of the most common tools is light. Photons are convenient because they interact weakly with their environment and can travel long distances without disturbance. Using carefully engineered crystals, a single incoming photon can be converted into two lower-energy photons whose properties are linked. Conservation laws ensure that certain combined quantities, such as polarization, are fixed for the pair. You rest with the calm understanding that nothing mystical happens here. The process is governed by known physical laws. The equipment is calibrated. The output is measured repeatedly. Each pair of photons emerges with a shared quantum description. Once created, the photons are sent in different directions. Optical fibers or free space paths guide them towards separate detectors. Along the way, scientists ensure that no unwanted signals leak between paths. The goal is isolation, not secrecy. Every possible classical explanation must be excluded by design. At each detector, a measurement device is placed. These devices can be rotated or adjusted to measure different properties. The choice of measurement setting is critical. In many experiments, the setting is chosen randomly and at the last possible moment, ensuring that no prior information could influence both sides. You notice how much attention is given to timing. Clocks are synchronized with extreme precision. Events are recorded with timestamps accurate to fractions of a billionth of a second. This allows scientists to determine whether any signal traveling at or below the speed of light could have influenced both measurements. If timing rules that out, the correlations cannot be explained by communication. Each detection event is simple. A signal either appears or it does not. A photon is registered with one outcome or another. On its own, each result looks random. There is no visible pattern. This randomness is expected and necessary. The structure appears only later, when data from both detectors are brought together and analyzed. Scientists compare long lists of outcomes, matching events that belong to the same photon pair. They calculate correlation statistics and test whether they match quantum predictions or classical limits. You rest with the fact that this analysis is not subjective. Mathematical criteria determine whether correlations violate Bell-type inequalities. The calculations are straightforward. Either the data fall within classical bounds or they do not. Over decades, experiments repeatedly show the same result. The correlations exceed what any local hidden variable model allows. The agreement with quantum theory is precise. Error margins shrink as techniques improve. You notice that these experiments are not isolated successes. They are replicated across different laboratories using different methods. Some use photons. Others use trapped ions, electrons, or atoms. The systems vary, but the underlying pattern remains. In experiments with trapped ions, particles are confined using electromagnetic fields. Lasers manipulate their internal states. Measurements are performed with high efficiency, reducing the chance that misdetections could bias results. These systems allow long interaction times and fine control. In solid-state experiments, entanglement is created between electrons or other quasiparticles inside carefully engineered materials. These setups operate at extremely low temperatures to reduce thermal noise. The goal remains the same: isolate the quantum system and measure correlations faithfully. You sense how much effort goes into closing loopholes. Early experiments leave room for doubt because detectors miss some events, or because settings are not fully independent. Later experiments address these concerns systematically. Detector efficiency improves. Randomness sources become more reliable. Separation distances increase. Eventually, experiments are designed that close all major loopholes at once. The results still support quantum predictions. At this point, confidence does not rest on any single experiment, but on the convergence of many. You remain grounded in the idea that laboratory testing is not about proving a belief. It is about ruling out alternatives. Each experiment narrows the range of explanations consistent with the data. Classical models fall away because they cannot account for what is observed. You also notice how cautious scientists remain. Claims are limited to what is measured. Language avoids exaggeration. Results are reported with uncertainties. Independent verification is required before conclusions are accepted. Entanglement experiments are often quiet affairs. They involve long periods of data collection, calibration, and analysis. Progress is measured in improved precision rather than dramatic discovery. This steady pace is a strength, not a weakness. As your breathing slows, you reflect on how these experiments transform abstract ideas into concrete evidence. Entanglement is not inferred from single events. It is revealed through patterns that persist across thousands or millions of trials. You rest with the understanding that the laboratory does not create entanglement through observation. It reveals entanglement by allowing its statistical structure to emerge. The equipment does not impose correlations. It records them. You also notice that the same experiments that test entanglement now form the basis of new technologies. Quantum communication systems rely on the same principles. The laboratory becomes both a testing ground and a proving ground. Still, the primary lesson remains scientific. When conditions are controlled and assumptions are tested, nature responds consistently. Entanglement behaves as quantum mechanics predicts, no more and no less. As attention softens, you recognize that the confidence surrounding entanglement does not come from bold claims, but from quiet repetition. The same results appear under different conditions with different tools in different places. The laboratory becomes a place where subtle structure is made visible, not through force, but through patience. Each measurement adds a small piece to a larger picture that remains stable and coherent. You remain calm in the knowledge that nothing about entanglement escapes measurement. It does not hide behind interpretation. It shows itself in data, clearly and repeatedly, when experiments are designed with care. As instruments continue to refine what can be isolated and compared, you sense that the strength of entanglement lies not in dramatic effects, but in the quiet reliability with which its patterns emerge whenever nature is measured with sufficient care. You begin by letting go of the idea that entanglement exists only in rare or artificial situations. While laboratories provide controlled settings to study it directly, nature does not wait for instruments to behave quantum mechanically. Wherever particles interact at small scales, the same rules apply. Entanglement arises naturally as a consequence of interaction, structure, and conservation laws. You rest with the understanding that atoms themselves are not collections of independent parts. An atom consists of electrons bound to a nucleus, and the behavior of those electrons cannot be fully described one at a time. Their quantum states overlap and combine, forming shared descriptions that determine how the atom absorbs and emits light. These shared states are entangled in a precise, measurable sense. Spectroscopy provides clear evidence of this. When atoms emit light, the frequencies observed depend on the combined quantum states of electrons and nuclei. The patterns cannot be explained by assigning separate properties to each component. They require a joint description that reflects how the parts are linked. You notice that this is not speculative. Spectral lines are measured with extreme precision. Their positions, intensities, and splitting patterns match predictions derived from quantum models that include entanglement. Without it, the data would not make sense. As your attention settles, you consider molecules. When atoms bind together to form molecules, their electrons rearrange into shared orbitals. These orbitals belong to the molecule as a whole, not to any single atom. The electrons are entangled across the entire structure. This entanglement determines molecular shape, bond strength, and chemical reactivity. Every chemical reaction you encounter relies on this behavior. When molecules vibrate, rotate, or react, their quantum states involve correlated motion of multiple particles. The stability of matter depends on these correlations. Chemistry works because entanglement exists. You rest with the idea that solids extend this principle further. In a crystal lattice, enormous numbers of particles interact. Their collective behavior gives rise to properties like electrical conductivity, magnetism, and heat capacity. These properties are not predictable by treating particles independently. In certain materials, electrons become entangled across large regions. This collective behavior explains why some materials conduct electricity while others do not. It explains why some exhibit magnetism and others remain neutral. Measurements confirm these effects through observable quantities such as resistance and magnetic susceptibility. You notice that physicists do not always use the word entanglement in these contexts, but the mathematics reveals it clearly. The inability to factor a system into independent parts is a defining feature. The predictions match experiments with remarkable accuracy. As your breathing slows, you turn attention to magnetic materials. In many solids, electron spins interact strongly with one another. These interactions lead to ordered patterns at low temperatures. The resulting magnetic behavior depends on entangled spin states extending across the material. Neutron scattering experiments provide direct evidence. When neutrons pass through a magnetic material, the way they scatter reveals correlations between spins. The data show patterns that require entangled descriptions. These correlations are not artifacts of measurement. They persist as stable features of the material. You rest with the understanding that entanglement also appears in thermal properties. At very low temperatures, quantum correlations influence how heat flows through materials. Experiments confirm deviations from classical predictions that align precisely with quantum models. You consider biological systems carefully, remaining grounded in evidence. Some processes, such as energy transfer in photosynthetic complexes, show signatures consistent with quantum coherence and correlation. Research continues in this area, and conclusions are drawn cautiously. Where effects are confirmed, they are modest and transient, shaped by environmental interaction. You remain calm in recognizing the difference between established results and active investigation. Entanglement is firmly confirmed in physical systems like atoms, molecules, and solids. In more complex systems, its role is studied carefully without exaggeration. You notice how entanglement does not require isolation to exist, but isolation to be easily observed. In nature, interactions with the environment often degrade entanglement quickly. Even so, its influence remains detectable through averaged effects and collective behavior. You rest with the idea that entanglement is not fragile in the sense of being rare. It is fragile in the sense that it changes when systems interact with their surroundings. This sensitivity explains why macroscopic objects appear classical. Their quantum correlations are continually redistributed into the environment. This does not erase entanglement. It spreads it. The quantum description becomes too complex to track in detail, but its consequences remain embedded in material properties. You begin to sense that the laboratory does not create something unnatural. It isolates and simplifies what already exists everywhere. By stripping away excess interaction, experiments make visible what nature normally hides beneath complexity. You remain grounded in the idea that entanglement is not an exception to natural behavior. It is a basic feature of how matter organizes itself at small scales. The classical world emerges not because entanglement disappears, but because it becomes widely distributed. As your attention softens, you reflect on how this perspective reshapes understanding. Quantum mechanics does not describe a separate realm detached from daily experience. It describes the foundation upon which that experience rests. You rest in the quiet realization that every solid surface, every chemical bond, and every stable structure owes its existence to quantum relationships that include entanglement. The effects are not dramatic. They are reliable. Nature does not announce these connections. It expresses them through consistency. Measurements align with predictions. Materials behave as expected. Technology works. As you remain still, you sense that entanglement is less like a rare phenomenon and more like a background structure, shaping the behavior of matter without drawing attention to itself. As entanglement quietly shapes the stability and behavior of matter itself, you are left with the gentle understanding that the correlations revealed in experiments reflect a deeper order already present throughout the physical world. You begin by resting with a simple but powerful idea. Information is physical. It is not abstract or detached from matter. Every bit of information must be stored, transmitted, and processed by physical systems, and those systems obey the laws of physics. When those laws are quantum mechanical, information behaves differently. Classical information relies on bits that take definite values, often described as zeros or ones. These values are stored in physical states such as electrical charges or magnetic orientations. Quantum information extends this idea. It uses quantum states as carriers of information, and those states follow the same probabilistic rules you have already encountered. You allow this to settle gently. Quantum information does not replace classical information. It generalizes it. When quantum systems are large or heavily interacting with their environment, they behave classically. When they are small and well isolated, their full quantum structure becomes accessible. A quantum unit of information is often called a qubit. A qubit is not simply a 0 or a 1. It is a quantum state that can yield different outcomes when measured. The important point is not that it holds multiple values at once, but that it can encode information in ways classical bits cannot. Entanglement plays a central role here. When qubits are entangled, the information they carry cannot be described independently. The information resides in their joint state. This shared structure allows certain tasks to be performed more efficiently or more securely than classical methods allow. You rest with the idea that none of this violates physical law. Entanglement does not create information from nothing. It does not allow unlimited processing power. It changes how information is distributed across systems. One of the clearest demonstrations is quantum teleportation. Despite its name, nothing is transported instantaneously. No matter moves through space. Instead, the quantum state of one system is transferred to another distant system using a combination of entanglement and classical communication. The process begins with two systems that share an entangled state. One of these systems interacts locally with a third system whose state is to be transferred. A measurement is performed that combines information from both. The result of that measurement is then sent through ordinary communication channels. When the distant system receives this information, it applies a specific transformation. After this step, the distant system takes on the quantum state originally held by the third system. The original state is no longer present at its starting location. Conservation of information is preserved. You notice how carefully constrained this process is. Classical communication is required. The speed of light remains a limit. Entanglement alone does nothing. It enables the transfer only when combined with measured data. Another application is quantum cryptography. Here, entanglement allows the creation of shared random keys whose security rests on physical principles rather than computational difficulty. If an eavesdropper attempts to extract information, the correlations are disturbed in measurable ways. You rest with the fact that this is not theoretical. Secure communication systems based on quantum principles have been demonstrated over optical fibers and satellite links. Their security is guaranteed by the structure of quantum measurement, not by assumptions about future computing power. Entanglement also enables certain forms of distributed measurement. When sensors share entangled states, they can achieve sensitivities that exceed classical limits under specific conditions. These enhancements are modest and carefully bounded, but they are real and measurable. You remain grounded in the idea that these advantages do not scale without limit. Noise, decoherence, and imperfect control all impose strict constraints. Entanglement is difficult to create, difficult to maintain, and easy to degrade. These challenges define the pace of progress. Quantum computing is often discussed in this context, and you approach it carefully. Entanglement is a necessary ingredient for quantum computation, but it is not sufficient on its own. Algorithms that provide advantages rely on specific patterns of entanglement combined with precise control. Experiments demonstrate small-scale quantum processors that manipulate entangled qubits. These systems perform tasks that illustrate quantum principles clearly. Scaling them to practical sizes remains an engineering challenge rather than a conceptual one. You rest with the clarity that quantum information does not promise unlimited speed or universal advantage. It offers specialized capabilities for specific problems. Where it works because nature permits those correlations to be used reliably. Throughout all of this, physical limits remain intact. Energy must be supplied. Errors must be corrected. Classical systems remain essential. Quantum systems complement rather than replace them. You notice that the language used by scientists remains careful. Claims are tested incrementally. Performance is benchmarked against classical alternatives. Advantages are reported with uncertainty ranges and conditions. As your breathing slows, you reflect on how entanglement shifts the meaning of information itself. Information is no longer always localized. It can be shared across systems in ways that require joint description. This sharing is not optional. It follows from how quantum states behave. You remain calm in the understanding that none of these developments depend on interpretation. They depend on measurement, statistics, and repeatability. Devices either work as predicted or they do not. Entanglement-enabled protocols succeed because the underlying physics is reliable. You also sense how restraint shapes this field. No claim is accepted without demonstration. No possibility is extended beyond evidence. Progress is steady rather than dramatic. As attention softens, you recognize that quantum information reframes entanglement from something puzzling into something useful. It becomes a resource that can be consumed, distributed, and degraded. This behavior is governed by clear rules. You rest with the idea that usefulness does not diminish mystery, but it grounds it. When entanglement enables specific tasks under known conditions, it becomes part of applied physics rather than speculation. The structure remains the same. Shared quantum states encode correlations. Measurements reveal them. Classical communication completes the picture. In this quiet understanding, you see that entanglement does not grant access to hidden realms. It grants a deeper use of relationships already present in quantum systems. As information reveals itself to be inseparable from the physical systems that carry it, you are left with the steady realization that entanglement reshapes what can be shared and compared, while remaining firmly bound by the same limits that govern all measurable processes in nature. You begin by settling into a careful distinction. In quantum physics, an observer is not a mind influencing reality. An observer is any physical system capable of interacting with another and recording an outcome. A detector counts as an observer. A measuring device counts as an observer. Human awareness is not required for quantum events to occur. This distinction matters because it removes confusion early. Quantum mechanics does not suggest that consciousness shapes the universe. It describes how physical interactions produce measurable results. When a quantum system interacts with a measuring device, the combined system follows the same physical laws as everything else. You rest with the idea that measurement is not passive. At small scales, to measure a property is to interact with it. Energy is exchanged. Momentum is transferred. The measuring device becomes entangled with the system being measured. This entanglement is not philosophical. It is physical and unavoidable. In simple cases, this interaction produces a clear outcome. A detector registers a signal. A counter increments. A spot appears on a screen. The result is definite and stable. Repeating the same measurement many times produces a predictable distribution of outcomes, exactly as quantum theory predicts. When entanglement is involved, measurement gains an additional layer. If two particles share a joint quantum state, measuring one does not reveal a pre-existing value. It produces an outcome that is consistent with the structure of the shared state. At the same time, the range of possible outcomes for the other particle becomes constrained. You notice that nothing in this process requires an observer to know or understand the result. The physical interaction alone is sufficient. A detector left unattended still produces data. The correlations remain whether or not anyone looks at them immediately. This leads naturally to the concept of decoherence. Decoherence describes what happens when a quantum system interacts with its environment. The environment includes everything not explicitly controlled, such as surrounding particles, radiation, and thermal motion. When a system becomes entangled with many uncontrolled degrees of freedom, its quantum coherence spreads outward. Interference effects become impossible to observe locally. The system begins to behave in a way that matches classical expectations. You rest with the understanding that decoherence does not destroy quantum behavior. It redistributes it. The quantum correlations do not vanish. They become shared across so many components that tracking them becomes impractical. The appearance of classical certainty emerges naturally from this process. This explains why everyday objects do not display obvious quantum effects. They are constantly interacting with their environment. Their quantum states become entangled with countless surrounding systems almost instantly. As a result, their behavior appears stable and definite. You remain grounded in the idea that measurement does not introduce randomness into the universe. It reveals randomness that is already encoded in quantum probabilities. The uncertainty is not created by observation. It is a property of the quantum state itself. Entanglement clarifies this further. In an entangled system, individual outcomes are not determined in advance. Only the statistical relationships between outcomes are fixed. Measurement reveals one possible outcome, selected according to well-defined probabilities. You notice that this view avoids unnecessary interpretation. It does not require multiple worlds. It does not require special roles for observers. It relies only on physical interaction, probability, and statistical consistency. Experiments support this view strongly. Automated systems perform entanglement experiments without human intervention. Results are recorded, stored, and analyzed later. The correlations remain unchanged. The absence or presence of awareness makes no measurable difference. You rest with the clarity that the word observer can be misleading if taken too literally. In physics, it refers to interaction, not perception. Once this is understood, many apparent paradoxes dissolve. The structure of entanglement does not imply that reality is incomplete until someone looks. It implies that certain properties are not defined independently of interaction. They emerge when systems interact in specific ways. You consider how this aligns with earlier understanding. Quantum states encode probabilities. Measurement selects an outcome. Decoherence explains why outcomes remain stable afterward. Entanglement explains how outcomes across systems are related. Each part fits together without contradiction. The framework remains consistent and predictive. No additional assumptions are required. You also notice that physicists remain careful in how far they extend these ideas. They avoid claiming that quantum mechanics explains consciousness or perception. These topics lie outside its tested domain. The theory speaks only about measurable physical systems. This restraint is important, keeps the science grounded. It prevents speculation from filling gaps where evidence is absent. What quantum mechanics explains, it explains extremely well. What it does not explain, it leaves open. As your breathing slows, you reflect on how measurement feels less mysterious when stripped of metaphor. It is an interaction. Entanglement is a shared description. Decoherence is environmental coupling. Each term refers to a physical process that can be tested and modeled. You remain calm in the understanding that observers do not stand outside the universe. They are part of it. Measuring devices obey the same laws as the systems they measure. This symmetry removes the need for special rules. In this view, the universe does not wait to be observed. It evolves continuously according to physical law. Measurement events are simply points where information becomes accessible in stable form. You rest with the idea that entanglement does not blur reality. It sharpens the rules by which outcomes are related. It shows that certainty at small scales is collective rather than individual. As attention softens further, you sense that understanding measurement in this way prepares the ground for deeper questions, not about observers, but about how quantum descriptions fit into larger physical theories. As interaction replaces observation at the heart of measurement, you are left with the steady sense that entanglement reshapes how outcomes become defined, while the physical world continues to unfold without requiring anything beyond the laws that govern it. You settle into the understanding that physics, even at its most successful, is not complete. Quantum mechanics describes the behavior of matter and energy at small scales with extraordinary accuracy. General relativity describes gravity and spacetime at large scales with equal precision. Each theory has been tested repeatedly within its domain. Yet when these domains overlap, questions remain open. You rest with the idea that unanswered questions are not failures. They are markers of where knowledge ends and investigation begins. At these edges, scientists move slowly, guided by consistency, observation, and mathematical coherence. One such boundary appears where entanglement meets spacetime. Quantum mechanics treats entanglement as a property of quantum states, independent of distance. Relativity treats spacetime as a geometric structure that governs how events are ordered and how influences propagate. Each framework works exceptionally well on its own. Bringing them together remains an active area of research. You notice that this challenge is not new. For decades, physicists have searched for a theory that unifies gravity with quantum mechanics. The difficulty lies not in imagination, but in constraint. Any new theory must reproduce the successful predictions of both existing frameworks. It must match every experiment already performed. You remain grounded in what is known. Experiments confirm that entanglement respects relativistic causality. No signals travel faster than light. Space-time structure remains intact. At the same time, entanglement appears to encode relationships that do not depend on spatial separation in the usual way. This coexistence raises careful questions. How is entanglement represented in a fully relativistic description? Does spacetime emerge from more fundamental quantum relationships, or does it remain a separate structure? These questions are posed precisely without assuming answers. You rest with the fact that current research explores multiple approaches. Some investigate quantum fields in curved spacetime, where gravity affects quantum systems without requiring a full theory of quantum gravity. These studies produce testable predictions, such as subtle effects near strong gravitational fields. Other approaches attempt to describe spacetime itself as an emergent phenomenon. In these ideas, spacetime geometry arises from deeper quantum degrees of freedom. Entanglement plays a role in shaping how these degrees of freedom are connected. Where evidence exists, it is examined carefully. Where evidence does not yet exist, claims remain tentative. You notice how cautious language remains essential. Scientists distinguish between established results, mathematical consistency, and physical reality. A model can be elegant without being confirmed. Confirmation requires observation. You also consider black holes, where gravity and quantum effects both become significant. Observations show that black holes obey thermodynamic laws. They have entropy and temperature. These properties suggest a deep connection between gravity, information, and quantum mechanics. Entanglement appears in theoretical descriptions of black hole entropy, linking quantum correlations to the counting of microscopic states. These connections are mathematically compelling, but they remain difficult to test directly. They guide thinking without overstepping evidence. You rest with the idea that the frontier is not a single place. It is a collection of precise questions asked at the limits of measurement. Each question is framed so that future experiments might answer it. Another open area concerns how entanglement behaves in complex, many-body systems. While small systems are well understood, large interacting systems remain challenging. Understanding how entanglement spreads, persists, or becomes hidden in such systems is an active area of research. Experiments using ultra-cold atoms and engineered materials allow controlled study of these effects. Measurements reveal patterns that help refine theory. Progress is incremental and data-driven. You remain calm in recognizing that some questions may take decades to resolve. This timescale is normal in physics. Past breakthroughs often follow long periods of careful groundwork. You also notice that restraint protects science from speculation. Ideas are not promoted because they are appealing. They are pursued because they are consistent, constrained, and potentially testable. Where testability is lacking, claims remain clearly labeled as provisional. You rest with the understanding that uncertainty does not weaken confidence in what is already known. Quantum mechanics remains one of the most precisely tested theories in science. Its open questions do not undermine its reliability. They mark the edges of its applicability. You reflect on how this process contrasts with fantasy. There are no sudden leaps or dramatic revelations. Progress unfolds through refinement, correction, and deeper understanding. As your breathing slows, you sense that entanglement occupies a unique position. It is both well understood in laboratory settings and deeply connected to unresolved questions about the structure of reality. This dual role makes it a powerful guide for future inquiry. You remain grounded in the present state of knowledge. No experiment has shown violations of known physical laws. No observation demands abandoning relativity or quantum mechanics. The task is not to discard what works, but to understand how these frameworks fit together more completely. You notice how scientists remain comfortable with partial understanding. They do not fill gaps with narrative. They leave space for evidence to speak. This patience is not passive. It drives the design of new experiments, more sensitive instruments, and more precise measurements. Each step narrows uncertainty without overstating conclusions. You rest with the quiet confidence that open questions are signs of a living science. They reflect curiosity disciplined by method. They ensure that understanding continues to deepen rather than stagnate. As attention softens, you recognize that the frontier is not a boundary to be crossed, but a region to be explored slowly, with care and humility. As established knowledge meets unanswered structure, you are left with the calm awareness that the deepest questions in physics arise not from doubt in what is known, but from the steady desire to understand how reliable truths fit into an even larger whole. You rest in the understanding that nothing you have encountered requires mystery to remain unresolved. Each idea builds carefully on observation, measurement, and tested theory. The picture that emerges is not dramatic or chaotic. It is steady, restrained, and precise. At the smallest scales, the universe does not behave according to everyday intuition, yet it behaves consistently. Quantum mechanics does not replace order with uncertainty. It replaces absolute prediction with structured probability. Outcomes vary, but patterns persist. Statistics remain stable. Laws remain intact. You reflect on how entanglement fits into this picture. It does not introduce new forces or hidden influences. It describes how certain systems must be treated as wholes rather than as collections of independent parts. The connection lies not in space, but in description. This realization feels quieter than it first appears. Entanglement does not suggest that distant objects reach across the universe to affect one another. It suggests that when systems are prepared together, their properties cannot always be assigned separately. Measurement reveals relationships already encoded in the physical state. You remain grounded in the role of evidence. Every claim about entanglement rests on experiments that can be repeated. Correlations appear exactly where theory predicts. They vanish when conditions change. Nothing occurs without cause, and nothing exceeds physical limits. You notice how this view reshapes the meaning of connection. In daily experience, connection often implies contact, force, or exchange. In quantum physics, connection can mean shared structure. It can mean that information about outcomes is distributed across a system rather than stored in isolated parts. This does not weaken the concept of reality. It strengthens it by aligning description with observation. Instead of insisting that nature conform to classical expectations, physics adapts its language to match what measurement reveals. You rest with the idea that measurement itself is not an intrusion. It is part of how information becomes accessible. Interactions occur. Outcomes register. Data accumulates. The universe does not change its behavior in response to being studied. Continues to follow the same rules. Entanglement highlights this neutrality. It does not require attention. It does not depend on awareness. It persists in automated systems, in natural processes, and in environments far removed from human observation. You consider how this perspective dissolves confusion around the role of observers. There is no special boundary where physics ends and perception begins. Measuring devices, environments, and observers are all physical systems interacting according to the same laws. This continuity feels calming. There is no need for exceptions. No need for additional principles. The universe remains unified in its behavior, even as descriptions become more refined. You reflect on how this journey began with the limits of classical physics. Those limits did not signal failure. They signaled scale. Classical laws work where they should. Quantum laws take over where precision demands them. Neither framework replaces the other. Each explains its domain fully. Entanglement sits naturally within this layered understanding. It does not undermine classical reality. It explains why classical independence emerges when quantum correlations spread into the environment and become inaccessible. You remain calm in recognizing that what feels unfamiliar is not unstable. The quantum description is among the most reliable tools science has produced. Its predictions guide technologies that function with extraordinary accuracy. You notice how restraint has shaped every step. Claims are bounded. Language remains careful. Where knowledge ends, uncertainty is acknowledged openly. This honesty is not weakness. It is the strength of scientific understanding. As your breathing slows, you reflect on the idea of connection itself. In a scientific universe, connection does not imply intention or meaning. It implies structure. It implies lawful relationships governed by measurable rules. These relationships do not compete with human experience. They support it. The stability of matter, the reliability of technology, and the predictability of natural processes all arise from the same quantum foundations. You rest with the realization that understanding does not require the universe to feel familiar. It requires consistency. Entanglement is consistent. It behaves the same way every time the same conditions are met. This reliability allows curiosity to remain calm. There is no need to resolve every question immediately. Open areas of research remain active without threatening what is already known. You reflect on how science progresses not by closing questions, but by refining them. Each answer clarifies what can be asked next. Each experiment narrows uncertainty. Entanglement has followed this path. Once puzzling, it becomes measurable. Once debated, it becomes tested. Once abstract, it becomes useful. At every stage, evidence leads. You remain grounded in the idea that the universe does not conceal its workings. It reveals them gradually, through patterns that persist across time and space. As attention softens, you feel the calm coherence of a universe governed by rules that do not change in response to curiosity. They remain steady, whether observed or not. You rest with the understanding that connection, at its deepest level, is not something added to the universe. It is something discovered through careful measurement and honest description. In this view, entanglement does not make reality strange. It makes it more accurately known. As understanding settles into quiet clarity, you are left with the steady sense that connection in the universe is not imposed or imagined, but revealed through the simple consistency with which nature responds whenever it is measured with care.